into the center of the Earth. So it takes 5 minutes for a P wave to travel 20 degrees. Okay, that's the example we were just looking at for the Pakistan earthquake recorded at station GNI in Turkey. And 20 degrees is 2,200 kilometers, which is 1,400 miles. Okay, it takes about 20 minutes for a P wave to get to the other side of the globe. Just to give you a sense of how long it takes. It takes 20 minutes for a P wave to get to the other side of the globe. All right. So this is showing it on the globe. If you just drew it on a sort of flat Earth, like you're just thinking about a local problem in this little part of the Earth, you could think of it being like this. If you have some sort of explosive source, the energy would dive down into the Earth and then come back up to the surface. And the energy that goes to stations that are further away dives down deeper into the Earth. That's just the nature of the ray paths that the energy takes. Okay? This is the S-wave figure. I'm sorry, I was getting my two figures a little confused. So this shows that you only see S-waves out to about 105 degrees, and that's because the S-waves don't travel through this fluid outer core. Okay, so let's think about what the seismic energy would look like at the surface of the Earth. Now we understand the ray paths a little bit, and now we understand the particle motion a little bit. So let's start with a very simple explosive source, right? So an explosive source means it's all P waves. Because the explosive source, it just explodes, there's a push out, and so the motion, the particle motion, is in the same direction that the energy is traveling. The particle motion is in and out from the explosion, and obviously the energy is radiating outwards from the explosion. So it's all P waves. It's simplifying the problem. So if we have this explosive source, and we have an array of 6 stations, 3 on either side of the explosive source, what would you expect the waveform to look like at this first station right here? So you have an explosion. Okay, it pushes out to start with. That energy travels along this ray path. What would the seismogram look like at this station? It's not a complicated question. It's the answer that at least most of you are thinking right now. Yeah. Up and down. So explain to me what the particle motion at this point will look like. Up, okay. And which direction will it go first? Up, exactly. Okay. So what he was saying is that at this point, because the energy is coming up towards the surface of the Earth, the motion is going to be vertical. It's going to be an up-down motion, and the motion is going to go up first. Right? This is a key point. I hope everybody's following. So if this is an explosive source, right, it pushes out. So that pulse that is pushing out first travels along this ray path, and it's pushing out first means away from the source. So it goes along this ray path. When it gets here, pushing out first, away from the source means up first. So the first motion at this seismogram is going to be up, and then of course it's going to come back and it's going to wiggle a little bit. Okay? So that's exactly right. So the first motion is up, and then it kind of comes back, and then it goes back to 0. All right? Yeah. So this explosion, yeah, is on the think of it as being on the surface or just below the surface. Yeah, so the energy radiates out from this in all directions, right? So if we draw what the energy radiation pattern might look like, okay, so here is, and let's put the explosion right at the surface of the Earth. Okay, so you set off the explosion, and the energy is going to radiate out. So here's the pulse of energy radiating out, and it's going to continue radiating out like so. Okay, so this is the energy radiating out in the Earth's subsurface, and then the energy radiating out in the air above it is going to be like this. It's going to sort of similar kind of path. The reason I've drawn it differently is that the velocity of the energy traveling through the subsurface is faster than the velocity traveling through the Earth. Okay, all right. What does it look like at the second station? This station right here. Yeah. Okay, exactly the same. All right, and the third station, exactly the same, and the fourth station, exactly the same, and the fifth station, all right, you're getting it, and the sixth station, all right, thank you. Okay, so this is why this is the easiest possible scenario, okay? It's a simple explosive source, the energy goes outwards in all directions, that means every station in the Earth that records it is a first motion up, okay? Everybody gets it, right? Obviously it's going to get more complicated. Okay, so let's move on to a different location. Where's this? Wallace Creek. Okay, so Wallace Creek is on which fault? San Andreas Fault. Where is the San Andreas Fault? Where is California. Okay, we're getting funny now. Where is the San Andreas Fault on this map? Okay, this is the San Andreas Fault running right along here. Okay, so we're going to do exactly the same problem for an earthquake on the San Andreas Fault. Okay, so this is the fault. We're going to imagine an earthquake occurring right at Wallace Creek. This is, of course, a right lateral fault, so that means that this side of the fault, you can think of it just being this little patch of the fault is going to slip, not the entire fault. Just think of the earthquake occurring at this point, and the bit on this side is going to move to the right, and the piece on this side is going to move to the left. All right, everybody got it? So what does the waveform look like at this seismic station right here? First of all, somebody describe the path that the energy is going to take from here to here, just so we're all on the same page. Yeah. Exactly, okay. So when we were looking on the previous slide, we were looking at a vertical cross-section through the Earth. We're now looking at a map view, so we're looking down at the Earth. So the ray path, you can't draw it on this diagram. The energy is going to start here. It's going to dive down into the Earth, i.e. into, behind the board, and then come back up to the station right here. Okay, so the path is diving down and then coming up to the station. So what's the waveform going to look like at this station? So this piece of the fault is moving in this direction to the right. Anybody except these two guys? Come on. Yes. It's going to be horizontal. Why do you think horizontal? Because the Earth being shifted? Okay. So it's not horizontal. So again, the idea is the same geometry as last time. The ray path dives down into the Earth and then comes back up. So the ray path itself is going to still be coming up nearly vertically, for the sake of this problem, nearly vertically beneath this station. Yeah. So it's going to push the station into the exactly. So it's going to push the station as if it's coming out towards us, i.e. the first motion at this station is going to be up. Okay, exactly as it was in the case of the explosion, right? Because this is moving in this direction, so this part of the Earth's crust is moving kind of close to the direction that the energy is traveling in. So it's a pulse pushing outwards. That pulse is carried down into the Earth, comes up, and so it comes out towards us. So it's a vertical motion up. All right. So now what about this station here? Same thing. Should we take a vote? Anybody else? Yeah. Exactly. So the station is going to go down because the motion is in the opposite direction. That's right. So this piece of the crust here is moved this way. So this piece has moved away from this station. So it's in the opposite direction. So the first motion here is down. All right? And this station over here, first motion up, and this station here. Oh, there isn't another one. This station here, down. Okay? So now, unlike the explosive case where it was up everywhere, in this case, there are these four quadrants. And so if we draw another line, this quadrant, any station in this quadrant, first motion is up. Any station in this quadrant, first motion is down. First motion is up, and first motion is down. So now we can see that there is a pattern that we can use to start to say something about the nature of the earthquake. All right? And this is what we call a beach ball diagram. All right? So if we just now, the way we do these is the area, the quadrant in this case, where the first motion is up, we color them in black. The area where the first motion is down, we color in white. And so in this particular geometry for an earthquake, a right lateral strike-slip earthquake on the San Andreas fault, this is what this beach ball diagram looks like. Okay? But it's very easy to remember whether it's black or white. If you think about, in this case, for the station over here, which is a black quadrant, the energy goes down, and the station comes up towards you, hits you in the face, you have a black eye. Okay? So when it comes up towards you, it's black, and when it goes down, it's white. All right? So the point is that we can use seismic stations. Not only can we locate the earthquake, we can also understand the geometry of the motion on the fault. So even though we may not be anywhere near here, we could have stations on the other side of the globe, we can construct this beach ball diagram, and it tells us that that earthquake was on a tells us it was on a strike-slip fault. What we cannot do is we cannot tell whether it was a slip on a fault oriented in this direction or in this direction. So there is an ambiguity between a fault in this orientation and a fault in this orientation. They will give us the same signal. So we don't have a complete answer, but it's telling us about this is a strike-slip fault. All right? Oh, and it's called beach balls because if you look at this in 3 dimensions, it looks like a beach ball. Okay? All right, so that was a strike-slip fault. And you don't need to worry about how we construct these beach balls for other types of faults, but what I want you to do is recognize the pattern. So these two patterns are just mirror images of one another. They're obviously very different to the sort of cross-like pattern that we had for the strike-slip fault. And this with white in the middle is what we get for normal faults. When you have an extension environment, you end up with white in the middle, and when you have a compression environment, you end up with black in the middle. All right? So again, the point here is that we can use our network of seismometers around the globe to detect earthquakes wherever they may be, and we can determine if it was a strike-slip fault, a thrust fault, or a normal fault. Okay? So that tells us about whether the environment is a translational environment, San Andreas fault, whether it's a compressional environment like the Himalayas, compressional environment, a thrust fault like the Himalayas, or an extensional environment like mid-ocean ridges. Okay? So if we come back to this particular earthquake, now I'm going to ask you to tell me, what's going on? Here we go. What kind of fault do you think that this earthquake occurred on? So this is now a topography map. So this is high topography, this is low topography, this is in Pakistan. So what kind of fault? Oops. Sorry. Yeah, anybody want to guess? What kind of fault? So somebody explain to me how we know that this is a thrust fault by looking at this map. It's very straightforward. It's mountain building, right? If you want to generate mountains, you have to have a compressional environment. So if you see mountains, it means it's a thrust fault. So what kind of beach ball does that mean that we would expect? Black in the center, okay? So we would expect a beach ball that is black in the center like this. Now what would be the orientation of this beach ball? Actually, I didn't describe this. Sorry. So if I go back, I have to go back. So when you look at these beach balls, the orientation of the fault is like so. It's at the strike of the fault on a map. It goes from point to point. So for this particular beach ball, the strike of the fault would be oriented like this, and of course it's the same for this beach ball over here. Okay? So what I'm asking is in the case of Pakistan, this Pakistan earthquake, what would be the strike of the fault? What would be the orientation of the fault? I mean, it's not this. It's just what the beach ball would look like. I'm asking what would be the strike of the fault in this case. Exactly. So you're doing the right geometry. Can you explain why you're saying that? Exactly. So the strike of the fault is going to be parallel to the mountain front. Okay, so the strike of the fault is going to be like this. And so what's the orientation of the beach ball? You just have to rotate it. This would be the orientation of the fault. This is the orientation of the fault. So this is what the beach ball would look like. So not only is it telling us it's a compressional environment, it's telling us about the orientation of the compression. Okay, so the strike of the fault is like this. So the orientation of the compression is perpendicular to that, like this. Okay. Okay. So remote sensing of plate tectonics, we can identify strike-slip faults like the San Andreas. They have beach balls that look like this. Normal environments, normal faulting, such as mid-ocean ridges, they have beach balls like this. And then reverse and thrust type faulting, subduction zones have beach balls like this. Okay, and so the orientation of the beach ball is telling us about the strike and the dip of the faults, as well as whether it's a compression, an extension, or a translational diagram. So what type of faults do we have along the Mid-Atlantic Ridge? Normal faults. So what type of beach balls do we have? Wide in the center. And so here's a map that shows the beach balls for a whole bunch of earthquakes along the Mid-Atlantic Ridge, and you can see they all have white centers, and they're all oriented. So this is the orientation of the fault here. So they're all orientated. Of course, it winds around, but the north mid-ocean ridge is pretty much north-south, and these faults are all north-south. Okay, for a for a subduction zone is thrust faulting, and so the type of beach balls would be what? Black in the middle. And so here's a bunch of earthquakes along the subduction zone offshore of Mexico. They all have black in the middle, and again, the orientation of these faults is parallel to the subduction zone, exactly as we would expect. And then finally, on the San Andreas fault, beach balls. Yes, there's beach balls everywhere. What type of fault and what type of beach balls? Strike slip, which means the cross pattern, just like we saw for Wallace Creek. And so here's a map of all of the moment tensors that's beach balls for 1995. These are actually beach balls determined by Dov Drager's group, one of the professors here. And so are these all strike-slip faults? I heard a no, and I heard a yes, and then I heard not that one. That's right. So many of them are, right? So all of these ones in the Bay Area, for example, are cross-type beach balls. So these are what we would expect for strike-slip type faults. Some crosses up here, but there are exceptions like this one and like this one. Okay? So what's this beach ball? What type of faulting is this beach ball? It's a thrust. So what do you think that is? Mountains. And which mountains are they? Is this ringing a bell? The Sierras? Somebody said it's not the Sierras. San Andreas Mountains? I'm not sure there are any San Andreas Mountains. Santa Monica? Santa Barbara? Are we just throwing out place names? Okay, I think you're sort of getting the message. This is what we were talking about on Thursday, right? So this is not the Northridge earthquake. The Northridge earthquake was in 1994. This is actually an aftershock of the Northridge earthquake. Right, that's right. And so this is showing the orientation for a thrust fault, an aftershock of the Northridge earthquake. This is in the transverse ranges. Remember, there's a big bend on the San Andreas, so the San Andreas comes up here, it bends and then continues up here. And because of that bend, there is all this thrust faulting. That's what creates the transverse ranges, which includes the Santa Monica Mountains and the Santa Susana Mountains. Santa Barbara doesn't really fit in there, I'm afraid. And so that's what you're seeing. This is a thrust fault close to the location of the Northridge earthquake associated with the compression environment that has been created by the big bend in the San Andreas fault. Okay, I'm going to stop there, and we will continue on Thursday.